Hello, everyone. My name is Katie Emilio, and I'm a program engineer in the Professional Development Department at ACI. I'd like to welcome you to this webinar, High Volume Fly Ash Concrete for Structural Applications. We're glad that you could join us. ACI is an approved education provider for the American Institute of Architects, and this webinar has been approved for one learning unit. This webinar reviews the information found in ACI 232.3R-14, Report on High Volume Fly Ash Concrete for Structural Applications. Our learning objectives for this webinar are as shown on the screen. They are also shown in your handout. And now I'd like to introduce our speakers for today. Bruce Rami, PhD, PE, and Fellow of ACI, is the Vice President of Environmental Engineering at We Energies and is responsible for compliance, strategy and planning, mitigation and risk management, environmental permitting of new projects, compliance assurance and identification of new and/or enhanced means of benefiting the environment through the business practices of We Energies, the principal utility of Wisconsin Energy Corporation. Another speaker today is Michael Thomas, PhD, Professional Engineer and Fellow of ACI. He is a professor and department chair in the Department of Civil Engineering at the University of New Brunswick and a registered professional engineer in the province of New Brunswick. He has been working in the field of cement and concrete research since 1983. Dr. Thomas's main research interests are concrete durability and the use of industrial byproducts, including pozzolans and slag. Ivan Diaz-Loya is a research and developmental manager at Headwaters Resources in Taylorsville, Georgia. He is a member of ACI Committees 232, Fly Ash and Concrete, 240, Natural Pozzolans, and 236, Material Science of Concrete. He received his PhD from Louisiana Tech University. His research interests include fly ash reactivity in concrete, alternative supplementary cementitious materials, and reuse of coal combustion products. And now I will pass the presentation over to Ivan.
Thank you, Katie. Well, let's start with a definition, which is kind of a gray area. So what is high-volume fly ash concrete? ACI 232 defines it as concrete having a large replacement by mass of Portland cement with fly ash. But what is a large replacement? Malorda in 1986 defined high-volume fly ash as more than 50%. More recently, Rami and Taranail in 2000 defined high-volume fly ash concrete as more than 37%. Now, another definition is higher fly ash replacement than typical. And most would agree that typical would be considered up to 35%. So just to give you some historical background, Raymond Davis, professor from Berkeley, along with some of his colleagues, were the first to highlight the benefits of using fly ash up to 50%. The benefits they highlighted were lower heat of hydration and reduced potential for thermal cracking. Their findings were applied in the construction of the Hungry Horse Dam in Montana. Another example is the Stillwater Dam in Utah, which was built in 1980 with roller compacted concrete with a 40% fly ash replacement. Other applications of structures that have been built with high-volume fly ash concrete include roads, foundations, retaining walls, marine slipways, sewage treatment works, and concrete viaducts. And Bruce Rami will speak more about examples in field applications. So in recent decades, sustainability has been added as a major benefit of high-volume fly ash concrete, added to the lower heat of hydration and reduced potential for thermal cracking. Now, concrete has a relatively low embodied energy compared to other construction materials. However, it's the most common man-made material in the world, by volume, that is. That means that its environmental impact is greatly amplified due to the high volumes that are produced. And this embodied energy of concrete is a function of the Portland cement content in the mixture. And that's because close to a ton of CO2 is released for each ton of cement that is produced. This comes from the burning of gas or whatever it's being used to fire the kiln, and from the decomposition of calcium carbonate into calcium oxide and carbon dioxide. Different authors attribute anywhere from 4 to 8% of the global CO2 emissions to the production of Portland cement. So increasing the level, the replacement level of cement with fly ash significantly lowers the carbon footprint of concrete. It also reduces water usage since fly ash typically lowers the water demand. It also reduces the consumption of virgin materials that are necessary for the production of Portland cement, and increases concrete durability and service life, which is actually one of the most important factors because you're avoiding demolition and building new again with the carbon footprint that entails. High volume fly ash concrete can be split into two categories, general use and high performance. General use is typically adequate for requirements of 3,500 psi or less. It takes longer to set than regular concrete, and strength development is somewhat slower than conventional concrete. For this concrete, the strength requirements are typically extended to 56 days or 90 days, and it contains no water-reducing admixtures. High performance, on the other hand, requires the use of high-range water reducers and oftentimes accelerators. It can be used in structural applications. It can have the same set time and strength development as regular concrete, but it has very high long-term strength. Typically, the 1-year strength is double the 28-day strength. The durability benefits include high resistance to silt corrosion because of its low permeability, sulfate attack for the same reason, and ASR expansion because you essentially have a high amount of highly pozzolanic material. Either Class C or F can be used in high volume fly ash. However, most of the work to date has been done with Class F. The C618 requirements are the same for both, except for the main oxides. For Class F, it has to be at least 70%, and for Class C, 50%. Class F comes from bituminous or anthracite coal, while Class C comes from lignites or subbituminous coal. Class F has a low calcium content, while Class C has a much higher calcium content. As a result, Class F has pozzolanic properties, while Class C has pozzolanic and cementitious properties. Since Class C fly ash can add a significant amount of calcium or calcium aluminates to the system, the sulfate balance can be disrupted, which can potentially cause set time issues. For this reason, sulfate balance may need adjustment when using Class C fly ash at high replacement levels. So that's essentially why Class F is the most used type of fly ash that is used in high volume fly ash concrete. Some quick facts about high volume fly ash concrete and codes and specifications. ACI 318 does not limit the amount of fly ash in concrete except when concrete is exposed to de-icing salts. In this case, the maximum replacement allowed is 25%. If fly ash is pre-blended with cement, manufacturers can use ASTM C1157 and 1600, which are both performance-based specs, and thus do not limit fly ash replacement. Now, C595 can also be used, but this specification does limit fly ash replacement to 40%. Now, on an international context, European standard EN 197 allows up to 55% replacement of the type 4 cement, which is what they call a pozzolanic cement. These are the typical proportions for high volume fly ash concrete. Cementitious content going from 500 pounds to 675 pounds. In terms of water content, high performance concrete with high range water reducer will be closer to 200 pounds per cubic yard of water, while general use will be closer to 240 pounds per cubic yard. And high performance will most likely contain an accelerating admixture and a high-range water reducer. These are three examples of general use mixtures given by Mehta and Manmohan in 2006. These mixtures contain no water reducer. As a result, the water-cement ratio, or cementitious ratio, is between 0.38 and 0.44, as you can see, slightly higher, and the water content being between 200 and 230 pounds. And as you can see, the strength at 28 days is a little bit low, around 3,000 pounds, PSI, I'm sorry. But looking at the 90 days results, we see that it comes up to over 5,000 PSI. So these are very typical examples of a general use high volume fly ash concrete. Now these are two examples of high performance high volume fly ash concrete with high range water reducers. Now you can see that in these examples, the water to cementitious ratio is kept around 0.3, and the mixture has just 200 pounds of water, and as you can see, the strengths break 4,500 psi in 28 days, which is a typical requirement, in 5,500 psi in the case of mixture fly. So this lump is 4 to 5 inches, even though you have only 200 pounds of water in your mixture, with a water cementitious ratio of 0.3. And that's a big part because of the high-range water reducers that we see here. So some important characteristics to keep in mind in terms of workability. Class F fly ash reduces the water demand by around 4% for each 10% replacement of Portland cement. That means that if a conventional concrete mixture requires 300 pounds of water for a 3-inch lump, by replacing 50% of the cement with fly ash, you will reduce the water demand to 240 pounds to obtain the same slump, so around a 60-pound reduction. Set times are typically extended 2 to 3 hours, but this can be corrected with the use of admixtures such as calcium chloride and calcium nitrate, and there's a whole wide range of accelerators out there. They are actually not based on chlorides, or do not contain chlorides, which is a big drawback for many people. In general, Class F fly ash produces approximately half as much the heat of hydration as Portland cement. Therefore, concrete with a 50% fly ash replacement shows approximately 75% of the adiabatic temperature rise when compared to Portland cement concrete, or to regular concrete. So that's a 25% reduction, which is a big deal in terms of heat of hydration. Plastic shrinkage cracks, which are the cracks that develop while the mixture is still fresh, resulting from the evaporation of water from the pores of concrete, are more likely to occur in high volume fly ash concrete because of its relatively low water content. And that's it. With this, I finish my section of the webinar, and I'm going to pass on the control to Dr. Michael Thomas. He will be speaking about hardened properties and durability of high volume fly ash concrete.
Good afternoon, everyone. So I'm going to cover these topics in approximately the same order that they appear in the recent ACI 232 guide on high volume fly ash concrete. This is a sort of classic textbook effect that we see of high volume fly ash on strength. What we would tend to see is any sort of level of fly ash on strength, we see a depression in the initial early age at 1 or 2 days at 25%. Eventually, the strength will catch up, and the more fly ash we put in, the more we generally reduce the early age strength, and the longer it takes to catch up. But it does eventually catch up. Now, this is, as I say, it's a textbook effect if we actually produce concretes with equal water cementing materials ratio. I wanted to share some data with you from some research that was conducted by a consortium of CanMet and Hydro-Quebec in Canada, where they produced a number of very large monoliths, as you can see here, 8 by 13 by 16 feet. It had 2 control blocks and 3 blocks with 55% fly ash. I'm just using this as a demonstration. In this program here, they did, in addition to cast these monoliths, the main reason for casting them was to look at the temperature development and the risk of cracking as a result of the cooling from that autogenous temperature rise. So they cast a whole bunch of cylinders from these concretes as well, and I'm going to use them as an illustration of the mechanical properties of high volume fly ash concrete. What this graph shows here is a different approach to designing high volume fly ash concrete. The results for the control mix, the black circles with the gray infill, show the control mix. The blue triangles show a mix produced at roughly the same water cement to materials ratio, and they show that sort of classic response, with the early age strength being significantly reduced, especially at 1 day. These are strengths of cylinders, I should say, that were lab cured. But eventually the high volume fly ash mix catches up. Now, an alternative to this type of design is to design the high volume fly ash concrete with a lower water cement materials ratio, taking advantage of the ability of fly ash to lower the water content, lower the water demand, so you cast concrete with a lower water content, and also taking advantage of superplasticizer being used with that. And we can see here we actually get strength parity. We get much less reduction of early age strength. The concretes have parity in strength by about 28 days, and the longer term strength is much improved. So we can produce, even with high volumes of fly ash, 55%, by redesigning the mix, taking advantage of the water reduction and taking advantage of the effects of superplasticizer, we can actually get equivalent strength at relatively early age. One of the things we don't do enough of in North America is we concentrate on the properties of lab-cured cylinders to derive our strength. In situ strengths may be very much higher. Fly ash responds very well to the increase in temperature as a result of hydration. And what we're seeing here is some result. I should note this has been done at 30% fly ash. We need to conduct similar work at higher levels, but this is the kind of effect you get. On the left, we see the classic response fly ash having lower strength at 3 days, roughly equal strength at 28 days or 56 days, and much improved strength at 90 days. If we actually did temperature matched curing, what we would find is that by temperature match curing, we would actually match the temperature of our cylinders to the temperature that's being achieved in situ in a large pore. What we see is that the temperature match curing actually impairs the later age of Portland cement concrete, but much improves both the early age and the later age strength of fly ash concrete. So in situ, we may actually be getting equivalent strength at relatively early ages, even when we use a high volume of fly ash. So that's something that's worth considering. Moving on to looking at some other properties, splitting tensile strength. As I said, this paper by Baisillon, I'm just showing one paper from one type of research here. So this was these large monoliths with 55% fly ash. They tested both cylinders at all ages and cores taken from the blocks at various ages. And this shows the relationship between splitting tensile strength and the compressive strength of either the cores or the cylinders. What we see is the relationship is pretty much the same whether you've got fly ash or not. And we're going to see with this with some of the other mechanical properties that the mechanical properties will fall in line with the compressive strength. So if we see a reduction in strength, we'll see a reduction in compressive strength. We'll see a reduction in modulus, in tensile strength, and in flexure strength too. And we can use the same relationships that we typically use to predict these properties based on the compressive strength. Here's the relationship between the modulus of elasticity and the compressive strength, again, of either cores or cylinders. And what we see is, again, we see a single relationship. If anything, you could say that at higher strengths, the modulus is slightly lower for the Portland cement concrete than the fly ash concrete. And maybe at early ages, the modulus the modulus tends to be the same based on the compressive strength. The broken line in this case shows a typical relationship that's used to predict modulus based on the compressive strength. In units of megapascals, then the compressive strength is, the modulus is 5,000 times the square root of the compressive strength. And there's a very similar relationship, just a different constant for predicting it based on PSI. This graph here, we have less data here, but it shows the modulus of rupture or flexural strength as a function of the compressive strength, and again shows the typical relationships that are used to predict the flexure strength based on the compressive strength. And you can see, with one exception, the same relationship applies for fly ash that applies for Portland cement concrete. So just to wrap up on those properties, basically, you know, if you see an increase in compressive strength, you'll see an increase in the other mechanical properties. If you see a decrease in compressive strength, you'll see a reduction in the other mechanical properties. So strength remains a good predictor of the mechanical properties of the concrete, and the relationships used don't change regardless of whether you have 55% fly ash in there or not. Looking at creep is very difficult to look at creep because it really depends on things like when the concrete's loaded. If you load concrete at early age, you can get higher creep in fly ash concrete because it's going to have a lower strength at early age, so the stress-strength ratio is going to be increased. If you load concretes when they achieve the same strength, the creep of fly ash will be less long-term because of the significant long-term strength for the fly ash concrete during the test. So really it depends on the nature of the test. In ACI 232.2R, the following statement is made: the effects of fly ash on creep strain of concrete are limited primarily to the extent to which the fly ash influences the ultimate strength. So again, we're seeing the same effect of strength, that if you achieve equal strength, you'll achieve equal other mechanical properties. This statement is probably also true for concrete that contains other SCMs like slag or silica fume. Switching to durability, just to give you a summary on durability, generally high volume fly ash will be beneficial in terms of reducing the potential for cracking. This is largely due to the reduction in the heat produced. It's also a function of having a fairly low modulus at early age, which helps some of the shrinkage be relieved by creep. It will greatly benefit permeability. Class F fly ash will improve both alkali-silica reaction and sulfate attack, and the extent to, improve the resistance to chloride ion penetration, which reduces the risk of corrosion of reinforcement. And a general statement can be made that the higher the level of fly ash, the greater the benefit that's actually achieved in those properties listed on the left. Generally, fly ash content, high volume fly ash, has a neutral effect on freezing and thawing. That's the classic cyclic freezing and thawing in air-entrained concrete, and also on physical salt attack. But the Achilles heel here is that high volume fly ash may impair de-isosalt scaling and also impair carbonation, and carbonation is another means for inducing corrosion of reinforcement. The benefits almost undoubtedly outweigh the cons, if you like, in terms of performance and durability. Let's look at corrosion of steel in concrete. There are literally, and this is a picture that shows a pier in Florida in a marine environment after about 30 years of service. It's since been demolished at the age of about 35 years. Corrosion of steel in concrete, chloride-induced corrosion, is undoubtedly the #1 form of premature deterioration of reinforced concrete. Generally, concrete has a high pH, and it should protect steel from corrosion forever unless one or two things happen. One is that concrete chlorides from seawater or de-icing salts penetrate through the concrete cover and reach the steel, in which case corrosion of a rebar will happen and eventually the concrete will crack and spoil. The other process that is less talked about is the process of carbonation, where CO2 from the atmosphere penetrates through the concrete cover and reaches the still. And when that happens, it reduces the pH of the concrete around the still, and again, corrosion can occur. Carbonation is a much rarer form of deterioration than chlorides. I'm just going to look at two sets of data. The data I'm going to show you is my own because it was the easiest to show. This slide shows the performance of high volume fly ash concrete in a marine environment. What you see on the left, upper left, these are tanks that are in an estuarine condition, actually in the River Thames estuary in the United Kingdom. These concretes have been in this environment for 10 years when they were tested. They were tested by drilling the concrete samples and extracting dust and measuring the chloride content of that dust at different depths. They were also later tested to remove the steel and actually see how mass loss has occurred. I'm not going to be showing those data, but the profiles can be seen on the right. We have three different grades of concrete here, concrete with a specified strength of 25 MPa, 35 and 45 MPa. Please excuse the MPa units there, but 45 MPa is about 6,000, so 6,200 PSI. What we see is that in actual fact, in the concrete without fly ash, regardless of the strength of the concrete, the chlorides are penetrating fairly rapidly and reach a depth of 1 inch, which would be 25 millimeters on the axis, reach a very high level at the depth of 1 inch after just 10 years. The black dots below show the results for 50% fly ash, which show a much lower ingress of chlorides into these concretes after a 10-year period, again, regardless of the quality of the concrete. Fly ash really is extremely effective at reducing chloride ion penetration. And it becomes more effective the more fly ash that you have. This slide shows the results from rapid chloride permeability testing. This is the ASTM C1202 test, where we put 60 volts across a concrete sample for a 6-hour period, and we measure the charge passed in coulombs, and based on the amount of charge passed, we assign the concrete a high, moderate, low, very low, or negligible chloride ion permeability. On the right, I actually show how the Coulomb value of the concrete changes with time. Both the charge passed and the age of the concretes are shown on a log scale. What we see without any fly ash is the value starts off pretty high. It does get a little bit lower with age, but it's very, very difficult to achieve something below 1,500 coulombs. These are all 0.4 water cement ratios. So this is good quality concrete without fly ash, and it really is difficult to achieve a low coulomb value despite excessive maturity or a large degree of maturity. We can see that as we add fly ash at very early age, we might see small increases in the Coulomb value, especially at very early age. But the fly ash concrete gets better with age, and the rate at which it gets better with age increases with the fly ash content. By the time we get out to very mature concrete, concrete with 40 or 56% fly ash will achieve values, Coulomb values, below 100. Which is essentially a negligible chloride ion penetrability. So again, you can see the impact of fly ash there on chloride permeability. Alkali-silica reaction, there's literally hundreds of publications out there demonstrating that Class F fly ash is a very effective means of controlling ASR. The amount of fly ash you need varies depending on the reactivity of your aggregate, how much alkali is in the Portland cement, and some other parameters too. Generally, Class F fly ash, the more you put in, the more protection from ASR you'll get. With extremely reactive aggregates, you might need to go as high as 30 to 40%, maybe even higher. But generally, in most cases, 25 to 30% is enough to control ASR. Rather than show all the lab data, I'm just showing some examples of fill performance here. This is an exposure site in the UK. On the left, you have no fly ash. It's an 18-year-old concrete without fly ash. It's extensively cracked, as you can see. On the right, we have 25% fly ash with absolutely no cracking. As I said, with Class F fly ash, the more you put in, generally the more protection from ASR you're going to actually get. Here's an example of a real structure. On the right, we have a structure built with 20 to 30% fly ash, showing absolutely no signs of ASR after 40 years. This structure used a high alkali cement in combination with fly ash and was built with an aggregate that is a known ASR reactor. As you can see on the figure on the left is a dam without fly ash that shows very, very excessive cracking. Just a last field example, I like this one because these are 50-year-old dams. They used exactly the same aggregate. They were built as part of the same hydroelectric scheme. They used exactly the same aggregate. The one on the left used no fly ash. The one on the right used fly ash to control heat, and they also controlled ASR. They didn't know this would be the case when they constructed it, but it clearly has eliminated ASR. So Class F fly ash is known to be very effective. What this graph shows here is the results of a concrete prism test. This is a 2-year test for evaluating fly ash or slag or silica fume. The blue line showed Class F fly ash, showing 20 to 25 to 30% is effective in reducing the expansion at 2 years to less than the sort of specified maximum. When we move to Class C fly ash is less effective, and we may need in excess of 50% and maybe even 60% to control ASR expansion in the lab. So Class C fly ash is not as effective in this role. Sulfate resistance, again, there's literally hundreds of papers showing that Class F fly ash can mitigate sulfate attack. I'm just showing you a nice sort of pictorial representation of that. We have a type 1 ordinary Portland cement on the left that's been in sulfates for 5 years. It's extensively damaged. We can cure this damage or prevent it by using sulfate resisting, what's the type 5 cement, or we can cure it by actually taking the original type 1 cement and putting in sufficient Class F fly ash to control expansion. Again, with sulfate attack, the more fly ash you put in, the more protection you'll get. This just shows that the nature of the fly ash is important. What we're seeing here is expansion at 6 months in the ASTM C1012 test. And again, with the low calcium fly ashes, what we're seeing is very good control of sulfate attack. But as the fly ash content, as the calcium content of the fly ash gets higher, in other words, we move from an F ash to a C ash, the sulfate resistance gets inferior. And we can see very severe deterioration with a high level of Class C fly ash when we put it in a sulfate environment. So with both ASR and with sulfate attack, we have to remember that Class F fly ash is effective, very effective, and Class C fly ash less so. Deisosalt scaling, generally lab testing will show you that you get worse sulfate resistance, you get higher visual rating as you increase the fly ash content. And that just is shown here, 50% fly ash having very severe numerical scale ratings. If we looked at all the trends from lab tests, we would see that the effect of fly ash, basically scaling, increases with the water cementing material ratio, increases with the fly ash content. Once you get above 40 to 50%, generally the lab performance is quite inferior. The lab data generally supports the limits that ACI 318 imposes on concrete exposed to de-icing salts. And these are the limits. You'll see that we have a 25% maximum fly ash replacement level for concrete exposed to de-icing salts in 318. Now, I should say that I agree with this limit for what I call hand-finished flat work, concrete such as driveways and sidewalks. This is the type of concrete that we see most scaling. The field data generally indicate that both formed and slip-formed fly ash concrete can have a much greater resistance to scaling. I don't mean greater than a straight Portland cement, but certainly greater than hand-finished flat work. Here's an example of some hand-finished flat work. This is a sidewalk in Halifax, and you can see the difference after 12 winters between concrete without fly ash and 56% fly ash. However, there are literally hundreds of examples where slip-formed or formed concrete surfaces have survived many, many years with relatively high levels of fly ash. So it can be done. Now, you might think, well, 4 years or 6 years is not a very long time to test scaling, but generally with scaling, if you can see the isosalt scaling, you'll see it in the first year, definitely by the second year. If it survives 3 years without scaling, generally it won't scale. Finally, final thing I'll talk about is carbonation. At very high replacement levels of fly ash, in poorly cured concrete, you will see an increase in the depth of carbonation, and that's what this slide shows here. Carbonation is only really an issue when 2 or more of the following factors are involved. We have low strength, high water cement ratio concrete, poor initial moist curing, low depths of cover, and very high volumes of fly ash or slag. Consequently, this shouldn't be a deterrent to using high volumes of fly ash. When they are used, we have to ensure we have good quality concrete, adequate curing, and sufficient cover to the steel. I'm now going to pass on to Bruce Ramey. Thank you.
Well, thank you, Mike, and it's a great honor to be on this webinar with all of you this afternoon. High volume fly ash is my favorite topic, and I'm going to continue to follow the committee report with Chapter 6, which is on field applications, and then a little bit on sustainability. And so I don't forget it. The references that are listed are very valuable, especially if you haven't had experience with high volume fly ash before. And I just point you to there because we've had, in my opinion, a great record with over 25 years of use here at our company. And there's a wide range of applications. You've seen some examples already presented to you by the prior speakers. And one of the main things, I'm going to try and point out some learning experiences, from my work with high volume fly ash concrete. It's early involvement in projects, and pictured here on the screen right now are the Oak Creek expansion units. This is a relatively new power plant here at We Energies, and it's over a $2 billion project. And what was key here was sitting down with the design engineers and contractors very, very early in the planning to let them know we had an excellent source of fly ash right here and that we wanted to showcase it in our project. And again, with that early involvement, when you're not trying to change specifications later, you can jointly have a great success. And just about everything concrete in that photograph has fly ash in it, and some of it up to 50% of high volume fly ash concrete. The second slide here on field applications, the trial batches are essential. I can't overestimate this slide or emphasize it. The trial batches are going to save you a lot of headaches, when you go out into the field, and you have to be using the specific material combinations that you plan to work with. Someone changing, an admixture can have a very serious effect, on the performance of the concrete. And again, if you're doing something substantial, a field mock-up to have experience with the pumpability, finishability, the setting time, very connected to temperature, like all concrete, but probably even more sensitive in this case, and the increased pressure on formwork I'll be mentioning. So if you're just beginning to learn about high volume fly ash concrete, foundations are a good place to get your feet wet. Typically they don't require finishing. There's not a lot of times a requirement for early setting times, and sometimes these are considered mass concrete, where measures are needed to reduce the heat of hydration, and high volume fly ash concrete has that attribute as well. If you're going into something that requires trowel finishing, and whenever I hear trowel finishing, the first thing I ask is, do you really need a trowel finish? Because trowel finishing is an art, and sometimes this is overdone. But this can introduce some challenges with high volume fly ash concrete. It requires relatively short setting time to not delay the finishing, increases the propensity for plastic shrinkage cracking if the timing's off, the reduced rate of bleeding, because we're working typically with low water to cementitious materials ratio, can cause the surface to dry out early and encourage finishers to conduct finishing operations too early. So here we limit our fly ash content to 30 to 40% by mass of the total cementitious material when a trawl finish is needed. And again, it's special floors and things like that where it really is required. I put this photograph in here. This isn't a great glamorous project, but not all flat work requires a trawl finish, to make that point. And this is a high performance concrete slab on grade. And I just had it was an 8 cubic yard job. I think it's 8 inches thick. And what this was used for is a place for luggers and dumpsters where they'd be placed. And if you have any experience with that, they're dropped, the wheels get caught, you have gouging. So we wanted some high strength here. And this was over a 70% fly ash application in the concrete mixture that was used. And if you look in the background there, you'll actually see a controlled low-strength material buttress for the precast wall that's there that also worked out very well. Some other field applications, and I'm trying to get you to imagine the possibilities here of the high-volume fly ash concrete world. I have two things here. What we call an eco-pad. It's an in situ mixed concrete. This is a 3.5 acre storage pad in Kenosha, Wisconsin, and other projects have occurred since then, but half of it was with a cementitious content of 50% Class C fly ash, 50% Portland cement, and the other half was with actually slag cement, 50% and 50% Class C fly ash. And it continues to provide excellent performance. And alongside it here, I have a photograph of some paving bricks and other bricks from CalStar. And they use fly ash as the binder. So these are concrete products, and that have to meet high specifications for durability and strength. And their website is really a nice example for structures that have used these high volume fly ash concrete products, as well as how to show the sustainability and environmental performance attributes. Now, high volume fly ash concrete can exhibit self-consolidating behavior without excessive heat hydration. And so, a lot of times we're adding, super plasticizer, viscosity modifiers to get that type of self-consolidating concrete behavior. And so if you're working with that type of application, again, those trial batches are important to look at the admixture quantities that are needed, because typically this amount of fly ash will be very helpful in that regard. But once again, if you haven't worked with self-consolidating concrete, the formwork seals at joints need to be verified. And you have a very liquid performing material. And the addition of water at a job site is always bad, in my opinion, and it will decrease structural properties. And if additional workability is required, a small dose of compatible high-range water reducer can be added prior to placement. And this is a place where you have to really be paying attention to quality control. I had an experience with a ready-mix concrete truck delivery, and we needed to have a little more workability. And so we had high-range water reducer available at the truck, and it was added in a double dose. It put the concrete to sleep. I mean, it stayed green for a long time, and was not a good experience. Another one I'm going to mention is that when you're doing mass concrete, people are used to using retarding admixtures there to control that heat of hydration. And if you're working, again, with high volume fly ash concrete and somebody's messing with a retarder, you want to know ahead of time how that behaves. And I can think of a large foundation for a wind turbine that went in, and somebody had changed the admixture with good intentions, but again, they put that foundation to sleep for quite a long period of time. Eventually the strength came, but most of us wouldn't want to wait that long. Cold weather placement, this is even a more serious consideration when you're working with high volume fly ash applications. Less than 50 degrees Fahrenheit, expect a setting delay. You have to be patient, for the slower strength gain. You can do some things like using thermal blankets, especially with thin sections are more susceptible. And, there's other ways that you can mitigate with accelerating admixtures, the addition of heat, in aggregate or insulated forms. Hot weather placement, also an important consideration. Again, you're working with a concrete that typically has a low water to cementitious materials ratio. And so you want to restrict that loss of water due to evaporation and avoid that plastic shrinkage cracking. You can mitigate, if you're in a hot climate here, by placing the concrete at night, use of curing compounds, to try and keep the water in there where it's doing what it's needed to do, and covering with burlap or plastic sheets. Water fogging, if you're planning ahead, can be used to help increase humidity and reduce that evaporation. And again, the removal of forms, paying attention to the concrete strength that you need, and then continuing with that moist curing. Curing, hot weather placement is important, but for all of these concrete applications, I think Mike mentioned scaling resistance. One of the things we learned early on was to cure your concrete, because that will, in our case, has provided better performance. So the report also talks about barriers to use and some solutions. There's, a lot of times specifications are written prescriptively, so many pounds of this and so many pounds of that, versus a performance specification where you're looking for, a strength at a certain age or other properties. I think what we're doing today, trying to provide some informative, education information, and just having experience with it. It's not widespread out in the industry. Use of in-place strengths for the early age strength development, so you know what you're actually working with out there, especially when you're working with something new. Availability of fly ash. We're building we're a electric utility, a gas utility. We're building additional storage facilities to ensure that we have concrete quality fly ash available in the quantities needed. And there are beneficiation technologies out there that allow fly ash that maybe hasn't in the past been usable in concrete to convert it to something that is very usable. A lot of people look at this and they see it maybe as something they don't have experience with and see a higher cost. But again, our experience is that this is less than or equal to the cost of conventional concrete. Technical limitations, I think we heard about some of those, especially around durability. Those are all real considerations. I'm going to go back to the previous slide here. This is a picture of one of our storage facilities, and the ash recovery process shown is one where we take ash from the past and reburn it to produce new fly ash for concrete. So sometimes you'll hear little bits about 100% Class C fly ash concrete, and this is not in common use, and I would consider this experimental. It is covered briefly in the report, but this requires, admixtures to avoid a flash set in many cases. Experienced trials, mock-ups are required if you're going to go down this path. Understand the effects of temperature variation, those dosages, and the compatibility of the materials you're using. And use those specific materials when you're doing the trials. Don't be changing things. And I do recall early in my career about a fellow that tried this and rocked up a whole concrete mixer drum. You don't want to have that experience. Also gets very hot. So switching over to sustainability, I think we hear of LEED many times, and there are other rating systems out there, but they're really developed to provide an independent assessment of and evaluate the performance of buildings and the infrastructure. And when I think of sustainability, what I'm thinking about is making wise choices today to around conservation, efficient use of materials, so that the people that come after us have something yet to work with. Sustainability, typically there's 3 dimensions. You're looking at the economic, environmental, and social aspects of systems. And the rating systems have similarities. The reduced net embodied energy and carbon footprint are very important. Reducing resource depletion, transparency in these systems in reporting environmental impacts. And the ISO standards I have listed here provide some guidelines on sustainability and environmental product declarations. And typically there's a third-party verification involved. But embodied energy generally increases in direct proportion to its cement content. And the high-volume fly ash concrete mixtures offer a considerable benefit in this regard towards reducing the embodied energy and the carbon footprint. The lifespan, and this is really, if you do it right, you can increase the life of your structures. I know there's a bridge about 6 blocks from my office here that has a 75-year warranty on it. And yes, it does have fly ash in the concrete. As the lifespan of the structure increases, the ratio of that initial embodied energy to the total energy decreases because it's over a longer period of time, becomes less significant in comparison. The photograph that's embedded here in the slide is a business park from Sussex, Wisconsin, where they used one of these tax incremental financing districts, and it had a 30-year life requirement on it. And the original design that came in was asphalt. Well, most asphalt that I have experience with doesn't have a 30-year life. The solution was high-volume fly ash concrete for economic reasons, durability, and it's been performing out there for, I think, probably half of that life already. And again, embodied energy, concrete by volume is the most common man-made material in the world, and it has a relatively low embodied energy coefficient when you look at the mass and the volume. Again, the main source of CO2 emissions comes from the decarbonization of limestone during the manufacturing of Portland cement. There's about 10% addition here from the electric power use in the manufacture. And fly ash, again, using that, has low embodied energy because it is a byproduct of another industrial process. And just coming up in conclusion here, the benefits when you look at sustainability, I'm not going to read this list because you can all read, I think, but reduce CO2 emissions to conserving land and your natural resources, all very important. And the concrete benefits, to concrete as a material, fly ash and this high volume fly ash, just again, understanding your materials and how they work brings so much to the extended service life, and the longer it's out there, the less demolition that goes on and all of the issues associated with that. So my last slide is concrete opportunity, and I think I mentioned imagine the possibilities. So my question for all of you is, how will you make a difference with your work, for a sustainable environment by using high volume concrete for your projects? So thank you for your attention.
Thank you, Bruce. And now we'll take a couple questions that we received from the audience. Mike, you may want to address this one. If high volume fly ash is less permeable and less susceptible to freeze-thaw damage, how or why is high volume fly ash detrimental to de-icing and carbonation?
Okay, I think one of the reasons the reduction of distance to the isosol scaling in the laboratory is the general procedure is to cure, moist cure for 14 days and then dry for 14 days before starting the test. So the surface of the concrete only has 14 days curing and will be much weaker than than a Portland cement concrete of 14 days. So I think that's the main reason we see poor performance in the laboratory testing. With the hand-finished flat work, I think it really depends. I think there's a tendency for people to overwork the surface, bring bleed water to the surface, produce a relatively high water-cement ratio at the surface. One of the worst things is having a high slump concrete and using a vibrating screed to finish the surface, because you'll bring water to the surface and finish it in. That doesn't happen in slip form concrete because we tend to work with much drier mixers with very little sort of bleedable free water. And it doesn't happen with formed surfaces because we don't tend to create that weak layer of the surface with a formed surface. The carbonation issue, most carbonation tests are conducted with poorly cured concrete. So 1, 3, or 7 days moist curing, and then they're put in a relatively dry atmosphere, typically 65% humidity, to measure the depth of carbonation. And again, I think the reason we see poor carbonation resistance is because we're generally dealing with fairly poorly cured concrete, and the poor curing impacts the high volume fly ash more. In very well cured, mature concrete that's been exposed to moisture during service, or even without the deliberate moist curing, if it's exposed to moisture in service, it will still get better with age. We tend not to see significant carbonation.
Okay, thank you. Bruce, perhaps you could address this next question. The question is, are there any work or studies being done with high volume fly ash on masonry or CMU grout or mortar for tunnel use?
Well, I would say probably the place I would point you is to that CalStar website that I mentioned. I think if you Google that and go there, and you can send a question in. We are not, at my company, performing that type of research. We typically in tunnels are doing more cast in place type slip forming type of construction applications today.
Okay. Ivan, if you could address, there was a question, why is Class F fly ash more commonly used in high volume fly ash concrete?
Well, it's mainly because of the fact that Class C fly ash, when you use it in high volumes, you disrupt, or you can disrupt, your sulfate balance, or the cement sulfate balance. So that means that as you add Class C fly ash, you're adding calcium to the system. So initially, you retard the system, and then if you add enough Class C fly ash, enough calcium aluminate, you can actually have early stiffening or even flash set. So that's the main reason why. So you really want to do, if you're using Class C fly ash, you really want to do some trial batches and do some extensive testing before you actually go ahead with your project, or use it as an alternative mix, using a combination with Class F, for example, or 20% Class F or 20% Class C. That would be a good approach as well.
Okay. I'm not sure which of you would like to address this, but the question reads, when used for grouting, how can we accelerate the set time for underground work using a high volume fly ash concrete mix?
Well, this is Bruce Ramey. I would say Class C fly ash. Again, just based on Ivan's comment there, and doing some lab tests may perform very well for you in those type of applications.
Okay, and let's just look at one more question here. How common is the higher volume fly ash mixes at concrete plants? Are those readily available? Is that something you've had to seek out contractors that will do those mixes? What has your experience been?
I think it really depends on the ready-mix concrete producer that you're working with and their experience. I think if they have a silo for Class C or Class F fly ash, that you have a very good place to start there. And everyone's experience is different based on your part of the country. In our area here, Class C fly ash has been available for a long time, and there's a lot of experience with that. And the Class F fly ash would have to be brought in longer distances for the sulfate resistance or ASR concerns. We don't have a lot of that here. But again, it's the materials that you have available and the producer's experience that you're working with. Again, the trial batches go a long way. A small test slab and those kind of things are a good way to get started.
Okay, great. Go ahead.
I think I would just agree with Bruce said. I think most producers who are using fly ash are quite comfortable up to 30-35%. But if you want to go higher than that, then the producer, it's not difficult, but the producer really needs to do some trial batches and make sure he gets both the fresh and hardened concrete properties that are required for the job.
I agree with you, Mike, 100% on that. If I misspoke.
All right. Well, that's all the time we have today for questions. I want to thank everyone for attending and thank our presenters for taking the time out of their day to share this information on high volume fly ash with us. Thank you for joining us today. We hope you enjoyed the webinar.